merge, okay? This we discussed on the board. We have to sort both sides. Small sorts we could do in memory is relatively cheap. Very large tables become extremely expensive. Sometimes we can find an earlier step by either using an index access path, either as a range scan or a full scan on the index to redo the sorting on one or both sides. That will reduce the cost of the sort merge operation instead of doing real sorts on the data. Another way is we have to sort it in an earlier step for some reason. It makes this particular merge sort looks cheaper to it. So both of them need to be sorted by the join condition columns, by the keys. And then we just go through. The merge is actually very efficient, okay? So this was a little example of joining the department table to the employees again as an equal join, where A is greater, ename is greater than A. It decided to do this as a sort merge. You will see the sort on one or both sides. Sometimes it will do the merge without actually sorting because an earlier step, as I mentioned, provided. If the tables are big, the sort becomes expensive. We have to do it as a step that increases the cost of it. The next up is a hash join. The smallest row source generally is used to build a hash table because it takes less space in memory. The second row source, the larger one, is generally probed. If they're both the same size, it's a toss-up. It picks one of them to build it in memory. Okay? Once the hash table is built, probing it is very efficient. So we're doing a join of the order items to the inventory table as an equal join with our on condition. And it chose to do a hash join. It can do a full table scan on both sides. It can do an index on one side. Okay, and all it does is allows us to reduce the data. We could also, in some cases, find indexes on both sides. There's not required to have an index, but sometimes it's useful to have an index on other filters. This one doesn't have other filters, so it has to be an index on the join condition. But sometimes indexes on other filters can be used to reduce one side also. If we can make the table we're building the smallest by having good filters on it with other indexes, we can reduce the cost of building the hash table. But once the hash table is built, probing it is just like probing an index, but it's cheaper. It's just a mathematical calculation. A Cartesian cross product is done usually because of a mistake. The mistake in this query is we're joining two tables, but we never put the join condition in. We just put an additional filter. If you do that, it forces it to do a Cartesian cross product. Take every row from the worst one and join it from every row, but in reality, every employee does not work for every department. It doesn't really answer a sensible question. It was a mistake in the coding of the SQL. We missed the appropriate join condition, which is usually an equal join on the department number between the two of them. But if we leave it off, it can solve it as a Cartesian cross product. The bigger the tables are, the more expensive the Cartesian cross product. We did one optimization. It will take the smaller table, read it into memory, and it calls it a buffer operation with the sort. The sort means it's using the sort area as a buffer. Get this in memory. If I can get it all in memory, and then do a full table scan of this and look it up in memory, will be cheaper. And that was one operation. It doesn't really sort. It just uses it as a staging area to get all the rows before it starts it. And it was a little optimization, a way it processes Cartesian joins on the Oracle database server these days. The next up is looking at the join operations. We looked at equal joins, which are the most common and the easiest for the optimizer to join. Some people call them natural joins. I don't like the syntax for the natural join, but then that's just a Trevor thing. One of the problems I find, it hides the join condition. It's not explicitly mentioned in the statement, and then you have to go figure it out later. I think it's better to use a non-equal join or an equal join with the join. It's the equal joins we can do as natural joins. It's better to do it as a regular equal join. Specify an on or an using condition is nice with the new syntax. We also do outer joins, either left, right, or full. And this is one of the places where using the new syntax gives you a performance benefit. In the old syntax, to do a full join, we had to do a left union with the right. It took 2 passes of the data. We can now do the full join with 1 pass with a little optimization we put in. We do semi-joins for exist subqueries, and we do anti-joins for non-exist subqueries. Okay, so a join operation combines 2 output, 2 row sources into 1, producing a single row source. It's a merging of them. Okay, we're just putting back together what we separated as a sorted normal form as part of the data model for the database. It includes all of these mechanisms. The last one isn't a type of join. Okay, it's not really a join type. It's really an optimization for star schemas for reporting data warehousing. So equal joins, these are what the execution looks like, plans look like. We did a join between the employees and sale grade, and we did an equal join between the salary and the high salary. It chose to do it as a hash join. We did a non-equal join where we're joining the same 2 tables, but now we're looking at the salary between the low salary and the high salary. That's a non-equal join. It can't use a hash join to solve it. Hash joins can only be used for equal joins. It can do a sort merge or a nested loop. In this case, it chose a nested loop to solve it. The one advantage of the sort merge, it can solve all types of queries. Outer joins, an outer join returns a row if there is no match. Okay, there is a department 40 that doesn't have an employee in it. Normally when we do the equal join, we would just include the matches when I did my little example on the board. If we extend the employee table to have a fictitious row with all nulls and for every other column except for the department number, and pretend it matches 40, then it would allow us to include it. So we use outer joins to do it. And I really like the new syntax much better than the old. You say right, you take employee 1, right outer joined with the department. Okay, it did that as a sort merge. Okay, it can also solve that as using a hash join. It can also solve it using a nested loop. This because it's equivalent of a equal join with an extra row manufactured artificially for the employee table to make a join row to go with the department that has no rows. So we want to run the report that lists the departments and the employees, but it doesn't have one employee. We still want it to show up on the report as being a valid department with no employees. So we can use all 3 methods to solve that type of query. Semi-joins are used to match the first fast. Well, we want to know there is a match for department 10. We don't care which row it is or if there are multiple matches, just find the first one. So they are used for the exist. All we want to know, there is an employee that matches this condition and feed it to the other one. If there is none, then we stop the query. And it stops on the first match. So we can do that as a merge sort as a semi-join to COM. So we just wanted to show the different execution plans that could be used. Anti-joins are used to show what is the reverse of a regular join. In other words, show the row that has no matches when we join them together. Don't show every row including a fictitious row, just show the rows that when we join these two, that where the department doesn't have a match with the other one. We can implement that as an anti-join. It can be solved as a merge join. It can also be solved as a hash join. Okay, so we have a couple of ways we can actually do this. When you can see it done in both as a merge and a hash, and they will both say anti because they were done as an anti-join. So now we have a couple of questions for you. First up, the optimizer uses nested loop joins when joining a small number of rows with a good driving condition between two tables. And in particular, the good driving condition In particular, a good driving condition could be an index to probe. So I'll allow you to contemplate that for a moment. And the answer is true. If we have a good driving condition and we have an index to probe on one side, then it could make a good, efficient join method, especially if we don't have to probe too many too many rows in the index. It's also useful if we're want to return the first few rows the quickest. Okay. Next up is a little query that has a blank in it. The blank join is used when one or more of the tables do not have any join condition to any other table in the statement. Okay, so we give you 4 options. A, is it the hash? No. B, is it the Cartesian? Yes, if we leave off an equal join condition, it will do a Cartesian join. C, is non-equal join, is also not the choice, or outer join. So the choice is B, Cartesian. Next up is the blank join looks only for the first match. We'll let you contemplate the 4 answers. Notice they're different from the previous ones. And the answer is the semi-join looks for only the first match. Next up is another blank one you get to pick. Okay, in this case, in a hash join, the blank row source is used to build a hash table. We'll give you a moment to contemplate it. And the answer is B, the smallest. So it reads as, in a hash join, the smallest row source is used to build the hash table. That completes this lesson. We do have a short practice for you to have a look at the different join methods that we can use and explore where they give you better access paths, which ones are more ideal.